important processes in groundwater. That's one of them. Ion exchange, pyrite oxidation, sulfate reduction, and dissolution of minerals. We're going to take a look at them today to see how they influence the groundwater. This could be, for instance, the classical reaction of acid with the calcium carbonate, resulting in dissolution of calcium carbonate and resulting in a neutralization of the acid and increased hardness in the water. It could also be other minerals that are dissolved. Sometimes various salts can also be dissolved, and gypsum, and we have lots of stuff that could result in some changes in the groundwater composition. But this is definitely one of the important processes, and it could lead to things like this. These are some very vivid examples of calcium carbonate dissolution. They're called sinkholes. Experienced at some place where the underground is limestone or very calcareous soil, and over thousands and thousands of years you have had acid working with neutralizing and removing calcium carbonate from the subsoil, and all of a sudden you have a collapse of the structure, this calcareous soil, and the soil simply gives after and creates a big hole. Geologically, if you look at it, you can find some huge craters that are actually the results of such collapses, and sometimes you can see them just as small field where the soil very dramatically has collapsed, or it can even take place like up here. I think this spot is from Mexico, where all of a sudden you have a huge hole and a whole house could disappear down into the ground. So these are very dramatic results of mineral dissolution, but otherwise it's more of a process attacking small particles of calcium carbonate in the soil and neutralizing the acid. And the acid, where do we have sources of acid? We talked about it. We have these primary acids here, and resulting from the respective reactions mentioned here, carbonic acid, sulfuric acid, and nitric acid. And either of these acids can react with the calcium, but in different ways. So you can see here, if we have carbonic acid reacting with calcium carbonate, we have the reaction as Noelia and Michel wrote up before, where we have 1 mole of calcium formed for every 2 mole of hydrogen carbonate. If we have sulfuric acid, we will see the reaction can be written as this. Again, we produce dissolved calcium hardness, we produce hydrogen carbonate, and we have the sulfate. But now the ratio is 2 to 2. So the composition of the groundwater will be different. The ratio between calcium and bicarbonate will be different if the acidification and the hardness is a result of sulfuric acid. If we look at the last process down here, we also see from this one that nitric acid will lead to a 1-to-1 again, or just as for the sulfuric acid, at a molar ratio of 1 between calcium and bicarbonate. So if we look at things, we can take a look at this relationship and tell something about what kind of process was going on. That is embedded in this parameter called the degree of weathering, and I'll get back to that later. But the degree of weathering is looking at the concentration of calcium and magnesium in relation to concentration of hydrogen carbonate, and hence can tell us something. If it's high, well, we might have had some of these processes, the 2 lower ones going on. If it's low, well, this process upper one has dominated in the acidification and hardness formation. So results of calcium carbonate dissolution, we will get this increased hardness, and we will have a neutralization of this aggressive carbon dioxide. And what is aggressive carbon dioxide. It's carbon dioxide that has not had a chance to react, and hence is present as carbonic acid, well, as a result of you could say an oversaturation, where you have been producing CO2 and hence carbonic acid that has not yet reacted with anything. So if you take out groundwater typically from the upper layers, from above the acid front area, you wonder whether there's aggressive CO2, and one way to detect it is to take the water sample and add it to a piece of lime, so a piece of chalk, and you can see if you have a reaction that you can detect in bubbles. You can see CO2 being formed when the aggressive CO2 is reacting with the lime and producing CO2 gas. But there's also another way to look at it, and that's the calculation of this saturation index. So SI is the saturation index, and the saturation index is arrived at a complex looking at the chemistry with the CO2 and the potential reactions and the pH and so on. And if you have a chemical system in balance, then this saturation index, if you have aggressive CO2, so if you also say that the water is unsaturated, that is if the logarithm to the saturation index, this value calculated here, is less than 0. So yeah. So if you do have aggressive CO2, it's less than 0. So we can see if log SI is less than 0, that means that we are unsaturated, or that we have aggressive CO2. And if log SI is equal to 0, then there is no aggressive CO2. It shouldn't be possible to have a positive value, but the accuracy when we're measuring using concentrations, and the thing is that when we just calculated the and not taking into consideration effect of temperature and effect of sorting out, so the fact that we should really be using activity instead of concentration and so on, the accuracy is plus minus 0.5 or 1. So, but that means that if we see something that's -2 or -3, we can say pretty sure that we do have some aggressive CO2. But if it's just around 0, well, we can't really be sure looking at this. But it's a good indication to calculate this to see if we have aggressive CO2. And now I've got to move some of this because I have my next thing I wanted to show just is that's the carbonic system again written up. I've got down here. Okay, so mineral dissolution and calcium carbonate dissolution, one major process. The next process I'll get around is the ion exchange. So ion exchange is with these clay minerals that has a very big surface area. So clay minerals are very, very fine particles with a relatively or a very large surface area. And this surface area, there are some charges in the clay mineral that makes it possible for external ions to get associated and and bind to the clay. And when the clay was deposited, I don't know, millions of years ago, there was typically a salt water. For the Danish sediments, that was a salt water situation. So there was a natural equilibrium between the salt components of the water and the clay. So there is both a ratio of sodium to chloride that is natural in these sediments. And that means if we find groundwater with a different ratio of sodium to chloride, that's an indication that, well, we could have had some release of sodium from the clay to the water because we have had some ions with a stronger affinity for the sorption to the clay to replace the sodium. So as it's illustrated here, the calcium can take the place of two sodium ions and get tied up. It has a stronger affinity for the bonding between clay and the positive ion. But it's all a question of equilibrium. If we pour in a lot of salt again for some reason, if we draw up salt groundwater, then we will have release of the calcium again. So it's a balance. And you know it from ion exchange, you know it from your dishwasher machine, maybe if you've got one, or you fill in salt in a dishwasher because it has a resin to tie up. There's an ion exchange process going on where you're softening the water to avoid these white calcareous surfaces on the glass. So the calcium of the water and the hot water here in Aarhus is tied up in this resin in the dishwasher. And the way it's regenerated is that you take a strong salt solution and pour it around the resin, and that will get the calcium away from the resin and recharge the resin with sodium. But it takes a very high concentration of that to take place. So once in a while you regenerate it with the salt you add to the dishwashing machine, and you discharge some very salty water containing the calcium, and now your ion exchange resin is regenerated. So here clay is the ion exchange resin. So and well, this soil CEC that's mentioned down here is a measure of what type of clay have you got in the soil. What is the cation exchange capacity? That's something you can measure for a specific clay type. So it varies a lot. Some clay types has very good ion exchange capacity, and other clay types has less cation exchange capacity. And this order of how the ions are tied up, the propensity for this clay minerals to tie up with the ions, they have a preference for polyvalent iron. So aluminum will tie up very strongly. So it takes a very high salt concentration to replace aluminum. Aluminum will take the place of sodium, and then calcium is also tying up quite well. Magnesium. Then we go down to the monovalent iron. Potassium has a slightly stronger affinity than sodium. So the typical process going on is that we'll have polyvalent cations replacing sodium. And that means if we have ion exchange, we will see the water softened, and we will see an increased sodium concentration, and the ratio between sodium and chloride will get higher. So that's the ion exchange ratio. Organic matter can also act as the ion exchange agent. So we get this ion exchange or ion ratio here, sodium to chloride, and then we've got these sort of rule of thumbs. If we've got 0.6 to 0.9, this is the native ratio between sodium and chloride. But if it's different than this, well, then we have a sign of ion exchange going on, meaning that if it's high, we've got ion exchange. We can also have something that we call reverse ion exchange. And reverse ion exchange is, for instance, what happens if you have intrusion of salt water into an aquifer. High concentrations of sodium that can then release some of the ions tied in the clay, and then we will see a lowered ion exchange ratio. Then we will have a higher, a lower ion exchange ratio. Structure of the clay. Well, first of all, we have to remember that clay has a very poor hydraulic conductivity, right? So these processes, ion exchange is also something that indicate very old water, because it takes decades for the water to go through clay and to react with clay. So, but we won't see destruction of the minerals as such. It's just a reaction, and down in the soil we won't see. I mean, it's always water-filled clay. It has always got water in it. I mean, you can only dry out clay if you I mean, the clay minerals has such a good ability to tie up with water that it takes really a lot of energy to take the water away from the clay. So basically, in the soil, unless if it's topsoil and really dry period, we will always see the clay being wet. So no, it's not destroyed as such. No, and it's slow processes. So if we look at it, what's the results? We've got it here. Softening of the water for the ion exchange may cause sodium values to exceed drinking water limits. So in extreme cases, extreme ion exchange, we get really salty water. And sodium can be really tricky to deal with in a water treatment situation. You can't really remove sodium except by reverse osmosis, by membrane treatment, or if you want to evaporate water, but some kind of desalination process. So it's definitely not an easy problem to solve if you've got increased sodium levels. You may have an increased pH if hydrogen ions is exchanged, meaning that if you have a lot of acid formed, you have acid in the groundwater, the hydrogen ions can change place with the sodium ions, so the acid is tied up with the clay, and that means removal of acid from the water, and hence pH going up. So it can be a process resulting in alkaline waters also, and it indicates older water because it's a slow process. Those were two of the major soil processes I will go through today, but I think we need a break. Right, then I've already now begun looking into the next process and discussing this, which is the pyrite oxidation. So pyrite is a mineral that we call fool's gold. It looks like this. I don't know if you've seen it. You can sometimes see it in nature washed out in water, and it's really goldish, but it's a sulfur mineral. It's much lighter than gold, and it's consists of iron sulfide. So pyrite is found in most sediments in smaller concentrations, and even a small amount can have a great influence in the groundwater. So what causes the pyrite to become oxidized? Which things do you think can react with pyrite and oxidize it? Can you remember how can we oxidize this iron sulfide? What does it take? Any suggestions? Where do you think it takes place in the soil? In the topsoil and the very deep soil? It requires an oxidizing agent, right? That's sort of in the name. What's an oxidizing agent, Hjelmar? What could it be? Oxygen, yes. Oxygen could start the process. Nitrate as well. So those two components can cause the pyrite to become oxidized. So where do we see it? What causes the pyrite oxidation? Well, intensive agriculture with large amounts of nitrate leaching into the aquifer or down into the soil. That can cause the pyrite to be oxidized, and hence production of this sulfuric acid, and then hopefully neutralization of the acid and increased hardness. It could also be this: when we extract groundwater, we lower the water table. And lowering the water table will allow for atmospheric air to get into the soil matrix to some extent, depending on the kind of soil and geology, of course. But it's a process that could cause atmospheric air or oxygen-rich water to get in contact with the minerals and then to oxidize the pyrite. So if we start, sometimes when we start to see, when there's strong signs of pyrite oxidation, it could be related to strong, to a powerful extraction of groundwater from a well, that the groundwater cone is depressed, and hence that we start to see new reactions. So a response to that, if you see increasing sulfate levels in the water, that could also be resulting from this pyrite oxidation, then, well, if you lower the intake of groundwater, or if you look at your water balance and try to see if you can increase the water table again, then you can probably slow down the process again. So the results here, nitrate is removed from the water as a consequence of this. Increased level of sulfate, acid formed, and right here, large amount of acid. It doesn't take much pyrite to form significant amount of acids, and hence we get hard water if there are carbonates, and we get acidic water if there's no carbonate. And then we have this nickel that is associated with the pyrite minerals, and it's indicating younger water because it's a process that takes place in the upper parts of the soil column. And then we've got this degree of weathering that I just mentioned, and the typical level of these components in the water will give us a degree of weathering in the range of 1 to 1.3, and higher degree of weathering are signs of the pyrite oxidation, for instance. Ion exchange influences the degree of weathering as well, as we talked about. Ion exchange will remove the Let's see if I can just get that. So it will remove the calcium and the magnesium elements. Sulfate reduction, this process that can take place in the very reduced conditions, so in the low, deep wells, typically deep in the ground, when we have exploited all the other electron acceptors, meaning that we are definitely below the nitrate front, and now iron and magnesium is reduced as well, and then the next electron acceptor that the microbes are looking for is the sulfate, and they'll start to reduce the sulfate and turn it into sulfite. That will typically tie up with iron, not forming pyrite, but something similar. And the sulfate reduction is actually removing acid from the water. So it can increase the pH, but it can also affect the degree of weathering. Because the bicarbonate ion, the concentration of that is pH dependent. And if we start to have elevated pH, well, that there is a balance there. The sulfate reduction, let's take a look at it. So it's this process here, for instance, could be written like this. Organic matter can be written in many forms. This is a very, very simple organic structure, which is one carbon atom for one water molecule. So this is it's a product like sugar, and reacting with sulfate. Well, we have oxidation of the carbon to CO2 that will react with water. But so yeah, there you've got the explanation to why it affects the degree of weathering, because we are actually producing CO2 when we are reducing the sulfate. That's the prime reason. So we have more hydrogen carbonates being formed, and that will be affecting the degree of weathering. Right. And where does it take place? Well, it's very reduced conditions, and when there are organic matter present in the sediments, often younger layers, because if we go real deep, we get down into the tertiary period, well, then we don't really have any organic materials. The organic materials is associated with the warmer periods of the quaternary situation. So growth of organic material that has been deposited in the sediments, in the younger sediments, and it's associated with microorganisms. So we're back to the water type scheme here, and we can see sulfate reduction as going on in the lower part. So when we have sulfate reduction actually going on as we go down here, because we can see the level of sulfate is decreasing, but we only really see strong signs of it when we start to see the hydrogen sulfide formation. That's where we've got the process. Okay, and I've mentioned the results here. So level of sulfate decreases, hydrogen carbonate increasing, and the degree of weathering decreasing, and then we may see hydrogen sulfide in the water. Okay,